Good evening everyone, good evening. I welcome you all again to NEET Elite. I hope you guys are doing great. So people, just let me know in the chats first of all if I'm audible and visible to everyone. Hello Chitra, hi Sidra, hi Ishpreet, hello Nazma, hello Jabisha, hi Ashwarya, hi Urvija, hi Zahid, hi Bibek, welcome back everyone, welcome back, hi Sabita, hello Sahil, hello Urvija, hi Ubad, hi Fazan, walaikum assalam. So people, just let me know in the chats if I'm audible and visible to everyone, right? Give me some green signal from the chats. Yes. I'm doing good. My day was good, Ashwarya, my day was good. Perfect. Hello Danish. Hi Dilip. Welcome back everyone, welcome back. Hello Anushka. Welcome back everyone. Alright, so Danish is a new student. Welcome Danish. Perfect guys, so as you all must be knowing, in the last session of chemical bonding, we discussed about something called as hybridization, correct? Yeah. And in the tonight's session, what we are going to do is, we will be continuing with the hybridization and at the same time, we'll be discussing something called as dipole moment as well, which is again the very important topic from this chapter, right? So I'll be starting this session with the hybridization again, right? I'll be giving you some examples, right? And show you how to calculate the hybridization by steric number method. And then we'll come to the dipole moment in detail, yeah? So before starting the session, the ones who have just joined in, who are new to the channel, let me introduce myself. Well, people, my name is Wassim Sir and I'm your chemistry master teacher writer on this NEET Elite channel, yeah? The ones who have not liked the video yet, please do like the video, share the video with friends, do subscribe to the channel and do not forget to hit the bell icon so that you get the notification of every single session which I take live on this NEET Elite channel, yeah? So do like the video, share the video with friends and do subscribe to the channel as well. Surely Gautam will be doing D and F block elements as well. No issues. Everything will be done. Perfect. Yes, Rupa, you can watch it. You can watch it. Absolutely. Perfect, guys. So let me know in the chats if you guys are super duper excited about this session as well, right? Just let me know in the chats if you people are super duper excited about this session as well. Hello, Ashita. Hi, Prabha. Hello Mahek. Hello Akhila. Welcome back everyone. Hello Akash. Yes, metallurgy will be also done, Akash, no issues. Hello Sundar. Perfect guys, perfect. Alright, so let's get going then. Let's get started with something called as hybridization, right? And then we'll be moving to the dipole moment. Hybridization basically we discussed in the last session. And in the today's session, I'll be giving you certain illustrations, right? By means of which you'll get to know how to calculate hybridization of the molecule by steric number method, yeah? Okay. So let me take certain examples so that you can calculate the hybridization of the central atom of any molecule, yeah? Okay, let's take few examples. Anyways, you can give me some examples in the chats. You guys can give me certain examples in the chats. I'll be showing you how to calculate hybridization of those elements, those molecules, compounds, whatever. You can let me know in the chats. Alright, so let's start with, for example, PCl3. PCl3 is the first one which I'll be taking, right? After PCl3, I'll be taking, for example, H3O positive. After H3O positive, let me take NH4 positive. Right? After NH4 positive, let me take XeF4, right? Let's try to discuss the hybridization of these molecules first of all, right? Let's try to discuss these first, yeah? Have a look exactly, guys, how do we calculate it? In the last session also, I told you how to calculate it, right? Okay? And this is just the examples by means of which the method to calculate hybridization is going to be clear to you, yeah? Okay, someone is saying BCl3. All right, BCl3 also will be doing. BCl3. Any more molecules? You can come ahead. You can come up. Chalo, someone is saying CH3Cl. CH3Cl. Okay. Right. Someone is saying SF4. All right, SF4 will be also calculating. Anything else? Okay, someone is saying SF6. All right, SF6 will be also calculating. Okay, so let's get going then. Let's get started with PCl3 first of all. Have a look, guys. First of all, you should see which one is the central atom over here. This phosphorus is a central atom, correct? Less electronegative element is taken as the central atom, and phosphorus is less electronegative than that of chlorine, right? So phosphorus, I'll be taking the central atom. So first of all, how many valence electrons are present in this phosphorus? Phosphorus belongs to group 15 elements, right? It belongs to nitrogen family. And nitrogen family has got 5 electrons in its valence shell, right? So in case of phosphorus, there are some 5 valence electrons present. Yes. Now, first of all, I would want you guys to let me know how many sigma bonds are being formed in this case. As I've told you in the last session, the number of terminal atoms attached, always gives the number of sigma bonds. So number of sigma bonds which are being formed in this case, in the current scenario, is 3, right? Number of sigma bonds. Now it's time to calculate the lone pairs on phosphorus. See guys, phosphorus is making some 3 bonds. It's making some 3 bonds with chlorine, correct? Phosphorus has some 5 valence electrons. Out of 5 valence electrons, this phosphorus is using 1, 2 and 3 for the bonding. Yes, out of 5 valence electrons, it's using 3 electrons for the bonding. So there'll be 2 electrons left as such on phosphorus in the form of a lone pair. So how many lone pairs are there with phosphorus? 1 lone pair, yes. So I got to know the number of sigma bonds, I got to know the number of lone pairs. So now I'll be calculating the steric number, which is simply sigma plus lone pair, right? Sigma is 3, lone pair is 1, so 3 plus 1 comes out to be 4, correct? If 3 plus 1 comes out to be 4, I'll simply say hybridization over here involved is sp3, yes. And if hybridization is sp3, the geometry is going to be tetrahedral. The geometry I'm talking about, I'm not talking about the shape. I'm talking about the geometry. Geometry is going to be tetrahedral in this case. I'm sure it's clear to everyone. Yeah. Let's talk about H3O positive as well. Have a look, guys, exactly how to calculate it. First of all, this oxygen is more electronegative, so this oxygen is going to be a central atom, right? So oxygen has some 6 valence electrons, as you all must be knowing. Yes, oxygen has some 6 valence electrons, correct? But there's a positive charge over here. So you need to subtract 1 electron from those 6. So 6 minus 1 comes out to be 5. So there are some 5 valence electrons with this oxygen right now. How many sigma bonds are being formed? Have a look. How many terminal atoms attached? 3. So sigma bonds are simply going to be 3, right? How many bonds this oxygen is forming? It's forming 3 bonds, right? So this oxygen, it had some 5 valence electrons, and out of 5 valence electrons, it is using some 3 valence electrons for the bonding. So there'll be 1 lone pair on the oxygen, right? There'll be 1 lone pair present on the oxygen, correct? So again, let's calculate the steric number. It's going to be 3 plus 1, that is 4. So again, the hybridization is sp3, yes. So what about the geometry? The geometry is again going to be tetrahedral only. Yes, tetrahedral geometry, I must say. Correct? Now, let's move on to something called as NH4 positive, right? NH4 positive. Have a look, guys, exactly. First of all, nitrogen is more electronegative, so it's my central atom. So valence electrons with nitrogen actually are 5, but there is a positive charge, so 5 minus 1 comes out to be 4, right? How many sigma bonds are being formed? Calculate the terminal atoms, 4 terminal atoms. So number of sigma bonds are 4, right? So basically, there were some 4 valence electrons with this nitrogen carrying the positive charge, right? And it has used all the 4 valence electrons to form 4 sigma bonds, yes. So will be there any lone pair on nitrogen as such? There won't be any lone pair on nitrogen as such, right? Because it had 4 valence electrons and it is using all the 4 electrons to form 4 sigma bonds, yeah? So no lone pair on this nitrogen. If there isn't any lone pair on nitrogen, I'll say the steric number is sigma plus lone pair, 4 plus 0 comes out to be 4. Again, the hybridization is sp3. Again, the geometry is going to be tetrahedral, right? Again, the geometry is going to be tetrahedral. I'm sure it's clear to everyone. Yeah? Now, similarly, guys, the next is XCF4, right? The next is XEF4. XCF4, right? Have a look. First of all, if you look at this xenon, xenon belongs to group 18 elements, right? It's a noble gas. Yes? And noble gases, they have got some 8 valence electrons, as you all must know. They have got some 8 valence electrons, as you all must know, right? And this xenon, how many sigma bonds it's forming? Calculate the terminal atoms, that are 4. So xenon is forming 4 sigma bonds, right? See guys, I'm making its rough structure. Xenon is forming some 4 sigma bonds, right? 1, 2, 3, 4. 4 sigma bonds with what? With fluorine, right? Since it had some 8 valence electrons, and out of 8 valence electrons, it's using 1, 2, 3 and 4, right? Out of 8 valence electrons, it is using 4 valence electrons for the bond formation. So there will be some 4 electrons left as such on xenon in the form of 2 lone pairs, right? So there are 2 lone pairs present on xenon as such. So lone pairs are 2, sigma bonds are 4. Now let's calculate the steric number. Steric number is simply going to be sigma plus lone pair, 4 plus 2, 6. And if steric number is 6, as you all must be knowing, it's going to be sp3d2, right? And which d orbitals are involved in the hybridization in case of sp3d2? It's going to be dz square and dx square minus y square. These 2 d orbitals are basically involved in the intermixing, right? In case of sp3d2 hybridization. I'm sure it's clear to everyone. You can let me know in the chats. Yeah? Right? Yes? So what is going to be the geometry of this molecule? The geometry of this molecule is going to be octahedral, right? As I've told in the last session, if the hybridization is sp3d2, the geometry is going to be octahedral, as simple as that. Right? Let's take a few more examples so that it becomes clear to you, right? The examples which you guys have provided to me, let's try to do those examples so that it becomes properly clear to you, yeah? Okay. Someone is saying calculate the hybridization of boron in BCl3, right? BCl3 is the compound which is given to me. First of all, this boron is the central atom, right? Boron is a group 13 element, and all the group 13 elements, they have got 3 electrons in their valence shell. So how many valence electrons are there with boron? There are some 3 valence electrons with boron. How many terminal atoms do we have? 3. So how many sigma bonds will be there? 3. So since it had some 3 valence electrons, and it is using all the 3 valence electrons to form 3 sigma bonds. Yes. So will there be any lone pair on boron? No way. There won't be any lone pair on boron. You got to know the sigma bonds, you got to know the lone pairs, calculate the steric number, 3 plus 0 comes out to be 3. If steric number is 3, the hybridization is going to be sp2, right? So the geometry is going to be trigonal planar. It's going to be trigonal planar. Yes, as simple as that. Right, people? Okay. CH3Cl, correct? CH3Cl. See, guys. Anyways, if I make CH3Cl, for example, right? If I make, for example, CH3Cl, it's forming, carbon is forming 4 bonds, right? 1, 2, 3, 4. 4 bonds it's forming. Rough structure I'm making, right? Since carbon has some 4 valence electrons, out of 4 valence electrons, it's using all these 4 valence electrons for the bonding, so there won't be any lone pair on carbon as such. So 4 plus 0 comes out to be 4. So hybridization is going to be sp3, right? It is simply sp3 hybridized, right? Yes, as simple as that. I'm sure it's clear to everyone. Yeah? Right, people? Similarly, let's calculate the hybridization over here in this molecule. It's SF4, correct? It is SF4. SF4. This sulfur is the central atom. Since sulfur, it belongs to group 16 elements, right? It belongs to oxygen family. And oxygen family has got some 6 valence electrons. Oxygen family I'm talking about, right? 6 valence electrons. Out of 6 valence electrons, it is using 4 valence electrons to form 4 sigma bonds. So there'll be 2 electrons left as such on sulfur in the form of a lone pair. So lone pairs on sulfur is going to be 1. How many sigma bonds are there? There are 4 sigma bonds. Terminal atoms are 4. So 4 plus 1 comes out to be 5. Steric number is going to be 5. And if the steric number is 5, the hybridization is going to be sp3d. And which d orbital is involved in the hybridization? It's going to be dz square, right? And we know if the hybridization is sp3d, what is going to be the geometry of the molecule? It's going to be the geometry I'm talking about, right? It's going to be trigonal bipyramidal, right? Trigonal bipyramidal. I'm sure it's clear to everyone. Now the last case which someone gave was SF6. Let's have a look on SF6 as well. Let's see the hybridization of it. Yes. Okay. So let's start with SF6. Again, the sulfur has got some 6 valence electrons. Out of 6, it is using all the 6 valence electrons to form 6 sigma bonds, right? Sulfur is forming 6 sigma bonds with fluorine, right? So people, it had some 6 valence electrons. Out of 6 valence electrons, it is using all the 6 valence electrons for the bonding. So there won't be any lone pair on sulfur. How many sigma bonds are there? 6. So lone pair plus sigma, 6 plus 0 comes out to be 6, so steric number is 6, and when the steric number is 6, hybridization is going to be sp3d2. And when the hybridization is sp3d2, the geometry is going to be octahedral if you remember. Yes? right? Now let me give you a few more important cases, yeah? Let me give you a few more important cases where pi bond gets formed, right? Where pi bond gets formed. See guys, let me take a few more important cases. For example, if I take the case of carbon dioxide, if I take the case of XeO2F2, right? If I take the case of XeOF4, these are some molecules which I'm taking over here, right? Let's have a look what happens to hybridization in these molecules. Have a look exactly, guys. First of all, carbon is attached with oxygen, right? And oxygen forms normally a double bond, correct? Oxygen forms normally a double bond. So if carbon is the central atom, how many valence electrons it has? It has got some 4 valence electrons, as you all must be knowing, right? If you know the structure of CO2, the structure oxygen forms double bond with carbon on both the sides. Yes. So out of 4 valence electrons, how many electrons it's using for bonding? 1, 2, 3, 4. So all the 4 valence electrons this carbon is using for bonding. So will there be any lone pair on carbon? There won't be any lone pair on carbon, right? There won't be any lone pair on carbon. How many sigma bonds are being formed? Right? See, total there are 4 bonds, but how many are sigma? I need to calculate sigma. 1 sigma, 2 sigma. There are only 2 sigma bonds. So what is the steric number? Steric number is equal to sigma plus lone pair. 2 plus 0 comes out to be 2. So hybridization is going to be sp. If the hybridization is sp, the geometry is going to be simply linear, right? As simple as that. Correct? Right? Absolutely, guys. Let's have a look on this one as well. XeO2F2, right? XeO2F2. First of all, xenon, which is the central atom, it has got some 8 valence electrons because it's a noble gas, right? It belongs to group 18 elements. So xenon is attached with 2 oxygen atoms and 2 fluorine atoms, right? So first of all, oxygen is going to form double bond with this xenon, right? And we have got 2 fluorine as well, which will be attached through a single bond, right? Right, people? Now have a look exactly. Oxygen had some 8 valence electrons. How many sigma bonds it's forming? How many sigma bonds it's forming? See, there is 1 sigma, 1 pi. 1 sigma, 1 pi. Sigma, sigma. 1, 2, 3, and 4. So 4 sigma bonds are being formed, simply. 4 sigma bonds are being formed. Right? Since it had some 8 valence electrons, and out of 8 valence electrons, how many it's using for bonding? 1, 2, 3, 4, 5, 6. So it is using some 6 valence electrons to form bonds, correct? So out of 8, if it is using 6, so there will be 2 electrons left as such on xenon in the form of lone pair. So how many lone pairs are there on xenon? 1 lone pair, correct? Let's calculate the steric number. Steric number is going to be 4 plus 1, 5. If steric number is 5, the hybridization will be sp3d. If hybridization is sp3d, what is going to be the geometry? The geometry is going to be trigonal bipyramidal. As simple as that, right? Yes? I'm sure it's clear to everyone, right, people? You can let me know in the chats if it's clear so that I can move on. All right, perfect. Okay, let's talk about this XeOF4 as well. Let's talk about this XeOF4 as well. See guys, xenon, again it has some 8 valence electrons, right? Let's make its rough structure. Xenon will be attached with oxygen through a double bond, and there are some 4 fluorine atoms as well. 1, 2, 3, and 4, correct? 8 valence electrons. How many sigma bonds are being formed? 1, 2, 3, 4, 5. So 5 sigma bonds are being formed. How many lone pairs are there with xenon? Have a look. Out of 8 valence electrons, it's using 1, 2, 3, 4, 5, 6, right? Yes. Out of 8 valence electrons, it's using 6 to form bonds, correct? So out of 8, it is using 6. There will be 2 electrons left as such on xenon in the form of a lone pair. So there is 1 lone pair. So 5 plus 1 comes out to be 6. If steric number is 6, so hybridization is going to be sp3d2, right? So the geometry of the molecule is going to be octahedral geometry molecule. Yes, I'm sure it's clear to every single guy. Yeah? Now you can give me some confirmation in the chat box if it's clear. And the ones who did not like the video, do like the video, share the video with your friends, and do not forget to subscribe to the channel as well. Yeah? So people, everything is clear? Everything is clear? Okay, let me give you one question. You guys let me know its answer, right? If I talk about SO2, what is the hybridization involved in this case? Let me know. I'm giving you 30 seconds to solve this one. SO2, let me know fast. SO2. Let me know fast. Yes, Vilas, exactly. Your test series and iconic batch. So people are saying it's sp2. Is that? Is that? I'm waiting for your answers. Okay, so let's check it out exactly. See, first of all, sulfur, it belongs to what? Group 16. Group 16 elements have got some 6 valence electrons, if you remember, oxygen family, correct? Sulfur is attached with oxygen, so double bond oxygen, correct? Now, out of 6 valence electrons, how many sigma bonds it's forming? Wait, how many sigma bonds the sulfur is forming? 1 sigma, 2 sigma. So, 2 sigma bonds the sulfur is forming, right? How many lone pairs are there on sulfur? Out of 6 valence electrons, it's using 1, 2, 3, 4. Out of 6 valence electrons, it's using 4. So, 2 electrons will be left as such on sulfur in the form of lone pair. So, lone pair is 1. So, 2 sigma bonds, 1 lone pair. What about the steric number? Steric number is going to be 2 plus 1. 2 plus 1 comes out to be 3. If steric number is 3, the hybridization is going to be simply sp2, correct? Right? If hybridization is sp2, its geometry is going to be what? It's going to be trigonal planar. Yes? Right, people? I'm sure it's clear to everyone, yeah? Okay? So, with this, your hybridization topic is done and dusted. Now, let's move on to the new topic, which is what we call as dipole moment, right? Dipole moment, people, dipole moment. Is everything clear? Just let me know in the chats first of all. If every single thing is clear, let me know in the chats, people. Then only I'll be moving on and talking about something called as dipole moment, right? Yes? All right. So, let's move on then to something called as dipole moment. Let's see exactly what this dipole moment is all about. Have a look, guys. Have a look exactly what this dipole moment is all about. See, guys. Let's assume I have got some 2 equal and opposite charges separated by certain distance. Let's say I've got 2 equal and opposite charges separated by certain distance A. Right? Let's assume that. We have got 2 equal and opposite charges separated by certain distance A. Right? This system containing 2 equal and opposite charges separated by certain distance A, this system of charges is what I'll be calling as dipole. It is one of the forms of the dipole, basically, right? It's one of the forms of the dipole, right? It's one of the types of the dipole, I must say. So dipole, I can define over here in chemistry, I can define it as whenever I'll be having 2 equal and opposite charges separated by certain distance, I'll be calling this system of charges as dipole, right? And for a dipole, we define a term called as dipole moment. For a dipole, we define a term called as dipole moment, which is denoted by mu, like this, dipole moment. Let me tell you, this dipole moment, how it's defined. It's defined as the product of, charge, product of charge, and the distance between the charges, Q multiplied by A, right? And let me tell you, this dipole moment, it is a vector quantity. It's a vector quantity. If it is a vector quantity, it will be definitely having the direction as well, right? And in chemistry, the direction of dipole moment is always taken from positive towards negative. The direction of dipole moment is always taken from positive towards negative. Yes? Okay? So whenever I'll be having, in chemistry I'm talking about, whenever I'll be having a system of equal and opposite charges separated by certain distance, I'll be calling this system of charges a dipole. And since for a dipole we define a term called as dipole moment, which is basically the product of charge and distance, and dipole moment is a vector quantity whose direction is from positive to negative in chemistry, right? Yes? Absolutely. Now we will have a look. This dipole moment, its units you are either going to take as, its units you can take it in dBi or you can take it in Coulomb meter, right? These are the units of dipole moment basically, which we'll be using in this chapter, right? And remember, 1 dBi, it is equal to 3.3 multiplied by 10 raised power 30 Coulomb meter, right? 1 dBi is equal to 3.3 into 10 raised power 30 coulomb meter. Do remember this as well, correct? Now, how am I going to use this concept and right? And where I'm going to use this concept in chemistry? Have a look, guys, exactly. Have a look exactly. For example, I'm taking a molecule as HCl. This is a molecule which I'm taking, H and Cl, right? H and Cl. Correct? Now, people, among these two elements, if I ask you which one is more electronegative, you'll say chlorine is more electronegative, right? It's a halogen, it's more electronegative. If chlorine is more electronegative, definitely you'll say it is going to attract the bonded pair of electron towards itself. If chlorine is attracting the bonded pair of electron towards itself, chlorine will be getting delta negative charge, hydrogen will be getting delta positive charge, right? So can I say I've got two equal and opposite charges separated by certain distance A? Absolutely. So is this molecule going to act like the dipole, right? It's a system of equal and opposite charges separated by certain distance A, so, right? So this molecule is behaving like the dipole, and for the dipole, what do? We calculate something called as dipole moment, right? Which is denoted like this. And this dipole moment is a vector quantity, correct? Whose direction is from positive to negative. So direction of dipole moment over here, which exists in, it's going to be in this way. And this dipole moment is nothing. It is the product of charge multiplied by distance between the two. That's all, right? Remember, if for any molecule, the net dipole moment is 0. If for any molecule, the net dipole, what is this net dipole moment? You'll understand it in some time. If for any molecule, net dipole moment is 0, we call that molecule as the non-polar molecule. I'll be giving you examples as well. And if for a molecule, the net dipole moment is non-zero, we call that molecule as the polar molecule. We call that as the polar molecule, correct? Yes? See, I told you the direction of dipole moment is from positive to negative, or you can say the direction of dipole moment is from less electronegative element to more electronegative element, right? Either you say the direction of dipole moment is from positive towards negative, or you can say the direction of dipole moment is from less electronegative element to more electronegative element. You can say it in this way as well, no issues, correct? Now guys, have a look. Let's say I'm taking a molecule as O2, or leave O2 aside, let me take the molecule as H2 for example, a simple molecule H2, right? If I'm taking a molecule H2, you all must be familiar with the structure. It's going to be H single bond H, correct? So on both the sides you have got hydrogen, right? Will there be the displacement of this electron pair towards any of the hydrogen? There won't be the displacement of electron pair towards any of the hydrogen, right? Because on both the sides you have got hydrogen atoms attached, right? Electronegativity difference right now is 0. If electronegativity difference is 0, so I'll say this electron pair is exactly going to be at the center. So if the electron pair is exactly at the center, if there is no displacement of the bonded pair of electron towards any of the atoms, will there be any charge on this? No. Will there be any charge on this? No. If there isn't any charge on any of the hydrogen atom, will it be acting like the dipole? No way. It won't be acting like a dipole. If it is not acting like a dipole, so its net dipole moment is 0. And if its net dipole moment is 0, it is going to be non-polar molecule. As simple as that, right? Similarly, if you take the case of F2 or O2, right? F2, O2, whatever, correct? Their net dipole moment is going to be 0. If their net dipole moment is 0, they are definitely going to be what? Non-polar molecules. As simple as that. Yeah? Similarly, let me take some cases of polar molecules as well. Polar molecules are the ones in which the net dipole moment is non-zero, correct? If I take the case of this HCl only, correct? This chlorine is more electronegative. It will attract the bonded pair of electrons towards itself, due to which this chlorine gets delta negative, hydrogen gets delta positive. So people, I got equal and opposite charges separated by certain distance, right? Equal and opposite charges separated by certain distance. So this molecule is right now behaving like the dipole, right? If it is behaving like the dipole, we can calculate its dipole moment, right? We can calculate its dipole moment. Its dipole moment is simply going to be what? Its dipole moment is going to be equal charge present on any one of them multiplied by distance, right? Okay. So if it is a dipole, the direction of dipole moment is going to be from positive to negative. So can I say this molecule has some net dipole moment? Absolutely. So net dipole moment of this molecule is non-zero. It is non-zero. If the net dipole moment of this molecule is non-zero, absolutely it's going to be the polar molecule, right? Yes. Absolutely. If you take the case of water, have a look. If I take the case of water, people, have a look exactly. Or let me not take the case of water, let me take a general example. This is B, this is A, and this is A, right? Let's assume B is more electronegative. If B is more electronegative than A, so B is going to attract this bonded pair of electron towards itself, due to which B gets delta negative, A gets delta positive. Similarly, due to this bond, B gets delta negative, A gets delta positive. So people, in this case, can I say I got two dipoles? This is one dipole, this one more dipole, correct? I got two dipoles. Yes. Now have a look. What is going to be the direction of this dipole moment? It's going to be from positive towards negative. Direction of this dipole moment, positive to negative, correct? So both the dipole moments are converging into the single direction. Both the ones are converging into the same direction, right? So the net dipole moment will be in this way. This is the net dipole moment, right? This is the net dipole moment, correct? Because these are vectors, right? You'll use the vector addition over here, right? So this is the direction of, for example, net dipole moment. So net dipole moment is coming out to be non-zero. So it's going to be a polar molecule, as simple as that, right? Remember one more thing. Lone pair also contributes towards the dipole. Lone pair on the atom also contributes towards the dipole moment, I must say. Towards the dipole moment. And the direction of the dipole moment, due to lone pair is always towards the lone pair, right? It's always towards the lone pair. For example, I'm taking the case of NH3. This is the NH3 molecule, right? This is the NH3 molecule. There is a lone pair on nitrogen as well. This is the lone pair on nitrogen, for example. Yes? This is the lone pair on nitrogen as well. First of all, I told you, lone pair also contributes towards the dipole moment. And the dipole moment due to this lone pair is towards the lone pair in this way. This is the dipole moment due to the lone pair, right? Yes? Now check the rest. Nitrogen and hydrogen. More electronegative is nitrogen. So nitrogen gets delta negative, hydrogen gets delta positive. So I got one dipole over here whose direction is going to be in this way, correct? Similarly, the direction of the dipole moment due to this bond is going to be in this way. Similarly, direction of the dipole moment due to this bond is going to be in this way, correct? So we have got basically four dipole moments, one pointing in this way, one pointing in this way, one pointing, for example, in this way, and one is already on the top. So four vectors are basically pointing towards single direction. So what is going to be the direction of the net dipole moment? It's going to be in this way. This is the direction of net dipole moment. So net dipole moment of this molecule is again non-zero. So this molecule is going to be polar, right? Yes. Right, people? Let me take the examples, the questions, I must say, by means of which this concept is going to get clear to you, right? Have a look, guys. Wait. The product of the magnitude of charge and the distance between the centers of the positive and negative charge is called as dipole moment. Dipole moment is charge multiplied by distance of separation between the two, right? Presence of dipole moment is represented by a crossed arrow, right? Like this, correct? Whose direction is going to be either from positive to negative, or you can say from less electronegative element to more electronegative element, right? That's something which is discussed, right? This arrow symbolizes the direction of shift of electron density, right? Absolutely, people. This arrow is symbolizing the direction of shift of electron density. It means simply the electron density is more towards fluorine, because fluorine is more electronegative element. It has displaced the bonded pair of electron towards itself, right? They just wait for it. Okay. So let's try to solve some questions. By means of which your dipole moment is going to get clear, right? Have a look exactly. Someone is saying, sir, what about NH3 and NF3? Bro, this is the first example, NH3 and NF3, right? Have a look. So let's compare the dipole moments of these NH3 and NF3, right? Yes. See, guys, have a look. If I talk about the structure of NH3, yeah? I'm talking about the structure of NH3. This is N, correct? Lone pair on nitrogen. This is H. This is H, and this is H. This is the structure of NH3. What about the structure of NF3, right? This N, one fluorine, one more fluorine, one more fluorine over here, and this is the lone pair present on nitrogen. This NF3, NH3 and NF3, correct? Yes. Let's compare the dipole moment of the two. Have a look, guys. First of all, there is a lone pair on nitrogen, lone pair of nitrogen, both the ones. So lone pair also contributes towards the dipole moment. So the dipole moment direction due to lone pair is in this way. Similarly, over here it is in this way, right? Among nitrogen and hydrogen, nitrogen is more electronegative, due to which nitrogen gets negative, hydrogen gets positive. So positive towards negative. This is the direction of the dipole moment due to this bond. Similarly, this is going to be the direction of dipole moment due to this bond. Similarly, this is going to be the direction of dipole moments due to this bond. So all the dipole moments, basically they are moving into the same direction, right? So this is basically the net dipole moment over here. This is the net dipole moment over here, which I'm representing through this long arrow, right? Yes, you can say due to NH bond, from less electronegative to more electronegative is the direction of dipole moment, right? You can say in that way as well. Now similarly, if you talk about this NF3, guys, if you talk about this NF3, between nitrogen and fluorine, fluorine is more electronegative, and the direction of dipole moment is from less electronegative element to more electronegative element, in this way, similarly in this way, similarly in this way, right? So in this case, all the four dipole moments were pointing in the single direction, in the same direction. But over here, all the four dipole moments are not pointing in the same direction, right? So can I say these three are going to cancel the effect of this dipole? I mean, these three, they are pointing in the singles in the same direction, and this one is pointing up above, right? Upwards. So these three are going to cancel the effect of this one. So if I ask you, where is going to be the net dipole moment more? People just understand it like the vector form, right? Four vectors pointing in the same direction, and out of four, three vectors are pointing in the same direction and one vector is pointing opposite, correct? So over here, the net dipole moment is going to be less. So remember, in case of NF3, the net dipole moment is less than that of NH3, right? So NF3 has got less dipole moment than that of NH3. Yes? Right? That means NH3 has got more dipole moment than that of NF3. Similarly, let's have a look on the second case. See, guys. Before talking about the second case, let me tell you one more thing. I forgot to tell you one more thing, guys. I forgot to tell you one more thing, okay? Right? Before talking about the second example, let me go back and tell you one more thing. Let's say I'm taking certain hydrocarbons like this. It is carbon attached with carbon, and over here hydrogen. This is one more hydrogen. This is one more hydrogen. Over here carbon attached with three hydrogens like this. Similarly, I've got one more molecule, C double bond C. This hydrogen attached, this hydrogen attached, this is hydrogen attached, this hydrogen attached, right? Let's say I've got something like this, C triple bond C, hydrogen attached, this hydrogen attached, correct? Let's say I've got like this, CH3, this is C, this is some double bond O, this is OH, right? Let's say I've got something like this is CH3, this is C, this is double bond O, this is H. These are few molecules which I've taken, right? Yes? Have a look exactly. If I ask you, this carbon, how many sigma bonds it's forming? 1, 2, 3, 4. It's forming 4 sigma bonds. So its steric number is 4 because it does not have any lone pair. So steric number is 4, so its hybridization is simply sp3. Again, 4 sigma bonds means sp3. Right? What about this one? First sigma, second sigma, third sigma. So 3 sigma bonds. No lone pair. So steric number is 3, it's sp2. Even this is sp2. 3 sigma bonds only, right? If you talk about this one, 1 sigma, 2 sigma. So steric number 2, sp. Steric number 2, sp, right? What about this carbon? It's forming 4 sigma bonds, so it's sp3. What about this carbon? It's forming 1, 2, 3, 3 sigma bonds, so sp2. What about this carbon? It's forming 3 sigma bonds, sp2. This carbon is forming 4 sigma bonds, sp3, right? So from the structure itself, you can see the hybridization as well. Yeah? Just calculate the number of sigma bonds. Or if I talk about the nitrogen, in NH3, right? Yes? Have a look. Nitrogen has got 1 lone pair, so 3 sigma bonds, 1 lone pair. 3 plus 1 is 4, right? Steric number is 4, so its hybridization is sp3. If you talk about water, H2O, oxygen has got some 2 lone pairs, as you all must be knowing. So 2 sigma bonds, 2 lone pairs, so 2 plus 2 is 4. Steric number is 4. If steric number is 4, hybridization is sp3. Yes, as simple as that. Now guys, this one we already checked, right? NH3 has got more dipole moment than that of NF3. Now if you look at the second example, have a look on the second example, guys. This carbon, it's forming 3 sigma bonds, right? 3 sigma bonds, so sp2. It's going to be planar. sp2, correct? Trigonal planar. Even this carbon sp2, trigonal planar, right? Yes. So all the bonds, they are basically present on the same plane. They are basically present on the boards. All the bonds are present on the board, right? All the bonds over here, they're present on the board, correct? Yes. Now have a look. If you look at this bond, guys, carbon CCl, carbon chlorine. Chlorine is more electronegative, so this gets delta negative, this would get delta positive, right? Or you can say this CCl bond, it's acting like the dipole, and the direction of dipole moment is from less electronegative element to more electronegative element. Similarly, the direction of dipole moment is from less electronegative element to more electronegative element. So the direction of two dipole moments is in same way, right? So this is the net dipole moment direction. This is the net dipole moment direction, right? But if you look at this configuration, have a look. CCl, the direction of dipole moment is from less to more. Similarly, CCl, less to more. Both are in opposite direction. Both are in opposite direction, right? So if both are in opposite direction, can I say they are going to cancel the effect of each other, right? I'll say they are going to cancel the effect of each other. So which one will have more dipole moment? Absolutely, the first one will have more dipole moment, correct? The first one is going to have more dipole moment. Why is that? Because both the dipole moments are pointing in the same direction. Yeah? If you talk about HF, HCl, HBr and HI, now have a look. There will be charge minus delta on fluorine, minus delta on chlorine, minus delta on bromine, minus delta on iodine, right? Fluorine being the maximum electronegative element, right? So fluorine has got the maximum tendency to attract the bonded pair towards itself. So if I ask you, where will be the magnitude of charge more in all of these? Is the magnitude of charge going to be more on fluorine or chlorine or bromine or iodine? You will say the magnitude of charge is going to be more on fluorine because fluorine is more electronegative. It has got more tendency to attract the bonded pair of electron towards itself, yeah? So fluorine has got more charge, and we know dipole moment is the product of charge and distance. More the charge, more is going to be the dipole moment, right? As simple as that. So what is the order of the dipole moment? This is the order of the dipole moment, correct? Yes, as simple as that. Yes, people? Okay, few more examples, guys, few more examples. But before these examples, let me have some water first so that we can have it. Just a second, I'll see, do we have more examples to finish? Yes, we have got more examples to finish, all right. So these are the examples we are going to finish now. Okay. Let me tell you guys, this is something which you are going to discuss in GOC, which I'll be teaching you in GOC, right? Right? There is something called as electron displacement effects, right? Some of you must have heard about inductive effect, mesomeric effect, right? Hyperconjugation, everything. Plus H, plus M, minus I, minus M, right? Minus I, plus I. Some of you might have heard about that, right? But I'm not going to talk in terms of plus I, plus M, minus M, because I'm assuming you have not studied it yet. So I'm going to talk in terms of only electron withdrawing nature and electron donating nature, right? Remember, this CH3 when attached with benzene ring, it acts as the electron donating group. If this CH3 acts as the electron donating group, it gives away the electron density towards benzene. It gives the electron density towards chlorine. Towards this benzene ring. If this CH3, it gives the electron density towards the benzene ring, so I'll say it gets delta positive and this carbon of benzene ring gets delta negative, right? Similarly, this CH3 is pushing electron density towards that carbon. So itself it gets delta positive and this carbon gets delta negative. So two dipole moments I got, positive to negative. This is positive to negative. Both are equal and opposite. So what is going to be the net dipole moment over here? I'll say net dipole moment over here is going to be 0. Because both are going to cancel out the effect of each other, right? Similarly, if you look at this case, this electron donating, it will donate electrons towards the benzene ring. So itself it gets delta positive, this carbon gets delta negative. Similarly, what about this? This carbon gets delta positive, this gets delta negative. So over here I got a dipole, right? In which the direction of dipole moment is going to be in this way. What about this one? One more dipole. The direction of dipole is going to be this way, right? Since both these dipole moments, these are vectors basically, we can shift the vectors. You would have studied the shifting of vectors in your class 11 physics, right? We can shift the vectors. If I make this vector, I'm making somewhere here, right? This vector, I'm making somewhere here in this way only, right? What is the angle between the two? Angle between the two is around 120 degree, right? Angle between these two vectors is 120 degree, right? Right? If I talk about this one, electron donating. So delta positive, delta negative. Direction of dipole moment from positive to negative, the direction of dipole moment from positive to negative. Let me shift these vectors now. Let me shift these vectors. This vector I'm drawing over here somewhere, right? This vector I'm drawing in the same direction in this way. What is the angle between the two? 60 degree. 60 degree, right? Whenever the angle between the two dipole moments is less, just use the vector addition. Use the vector addition, right? See, this is a vector, this is a vector, right? This is a vector, this is a vector. The dipole moment due to this vector is, for example, mu1. Dipole moment of this vector is, for example, mu2, right? Angle is 120. What is going to be the resultant? It's going to be under root of mu1 square plus mu2 square plus 2 mu1 mu2 cos theta, cos of 120, as you all must be familiar with. But I'm not talking in terms of that, right? Let me tell you one simple way. If the angle between the two dipole moments is less, the resultant dipole moment is more. If the angle between the two dipole moments is more, the resultant dipole moment is less. See, among these two, wherever the angle between the two dipole moments is less, the resultant dipole moment is more. So in the third case, the dipole moment is maximum, followed by second, followed by first. In the first one, it is 0, right? This is the order of the dipole moments, 3, 2, 1. As simple as that, right? Yes? Let's have a look on the second one as well. Do let me know what is the order of the dipole moments in this way. I just want to hear it from you. What about the order of the dipole moments in the sixth case? Can you let me know fast? Let me know fast, guys. What about the order of dipole moments in this case? So I can see majority of the people are coming out with 1, 2, 3. Is that? Let's check it out. Let's check it out. See, guys. Over here we have got one CH3 group attached, one NO2 group attached. Let me tell you, CH3 is electron donating. This one is electron donating. NO2 is electron withdrawing. NO2 is electron withdrawing. Why this electron donating? Why this electron withdrawing? That's something which I'll be teaching you in GOC when I'll teach you the electron displacement effects, right? Okay? Right after this chapter maybe. After this chapter maybe I'll be starting GOC. Yes? Have a look, guys. If this is electron donating, so this CH3 is going to donate electrons towards the benzene ring, due to which it gets delta positive and this gets delta negative. As simple as that. The direction of dipole moment is from positive to negative. Similarly, it's withdrawing. This NO2 is withdrawing. It's going to withdraw the electrons from the benzene ring, due to which it gets delta negative, this gets delta positive. So the direction of dipole moment is in this way. So let me shift these vectors. One is downwards, I'm talking about this one, and one is in this way, right? What is the angle between the two? It's 120. It's 120, yeah? Similarly, this CH3, it's electron donating again. So this is delta positive, this is delta negative. So this is the direction of dipole moment. NO2, electron withdrawing. NO2 gets delta negative, this carbon gets delta positive. And this is the direction of the dipole moment. Let me shift the vectors. One is simply downwards, right? One is simply downwards and one is in this way, right? Angled 60 degree. Angle 60 degree, right? Have a look on this one. CH3, electron donating. So delta positive, this is delta negative, right? NO2, electron withdrawing. Delta negative, delta positive. This is the direction of this dipole moment from positive to negative. This is the direction of this dipole moment from positive to negative. What is the angle between these two vectors? Angle between these two vectors is 0, right? Minimum the angle between the vectors, maximum is the net dipole moment. So where is the net dipole moment more? Where is the net dipole moment maximum? Check it out. Where is the net dipole moment maximum? Where, people? So over here you can see the angle is least. So net dipole moment is maximum over here in this case. In the third one, the net dipole moment is maximum, right? And then angle, wherever angle is less, net dipole moment is more. So 3 to 1 is again going to be the order, right? 3 to 1 is again going to be the order, right? I'm sure it's clear to everyone. Yeah? Right, people? Okay, so let me take a few more examples. Let me see if you can solve these examples as well. Okay, this one is important. This one is important, guys. This one is important. See, normally, if I look at this question, I need to give the order of dipole moments. I'll say fluorine being more electronegative than chlorine, then bromine, then iodine. So fluorine will be having maximum charge among all the halogens. If fluorine is going to have maximum charge, so net dipole moment of this molecule should be maximum, right? But let me tell you, dipole moment only does not depend on charge. It depends on distance as well, right? So you have to take two factors into consideration, charge as well as distance. So overall, magnitude of the dipole moment is governed by two factors, charge as well as distance. Charge as well as distance, right? Right, people? Yeah? Now have a look. Now have a look. No doubt, over here the charge present is maximum, followed by this chlorine, followed by this bromine, followed by this iodine, correct? No doubt. As per charge factor, dipole moment of this molecule should be maximum. But, let me tell you, as per distance factor, dipole moment of this molecule should be maximum. As per distance factor, dipole moment of this molecule should be maximum. Correct? Basically, this dipole moment, it is governed by two factors, charge as well as distance, correct? So you have to see both the factors basically. And after seeing both the factors, let me tell you, the dipole moment of CH3Cl is maximum among all. The dipole moment of CH3Cl is maximum among all. Then comes CH3F, then comes CH3Br, right? Then comes CH3I. This is actual order. This is the actual order. This is something which I'll be teaching you in class 12 chemistry as well. Okay, dipole moment, whenever you need to see two factors, charge as well as distance, right? For this molecule, the magnitude of both charge and distance comes out to be maximum, due to which dipole moment of it is maximum, right? H2O and H2S. Now over here you can decide simply on the basis of charge. The bond is between oxygen and hydrogen. Oxygen and hydrogen. The bond is between sulfur and hydrogen. Oxygen being more electronegative, so oxygen will have more charge, so more dipole moment. NH3PH3. Bond is between nitrogen and hydrogen. Over here phosphorus and nitrogen. Nitrogen being more electronegative, so more charge on nitrogen. This is the order of dipole moment. Again, OH, NH. OH bond, NH bond. OH bond. Oxygen is more electronegative, oxygen will have more charge. This is the order of dipole moment. Yes? Simple. Right? Okay, these are two more cases and you guys are going to let me know the answers of these two cases in the comment section, right? This is your homework. Do let me know the dipole moment order in the comment box once the session ends, right? This was all about your dipole moment. I'm sure your concept of dipole moment is clear to everyone, right? Okay. Let me tell you, tomorrow at maybe at 6 p.m. or 9 p.m. I'm going to take this session on this channel, and tomorrow we are going to study one more important theory that's called as VSEPR, valence shell, electron pair, repulsion theory. We are going to discuss in the tomorrow session, right, on NEET channel. And tonight on Enthuse channel, I'm going to take the session on chemical equilibrium, right? It's going to be the third session from the chapter, right? Yes? Okay, tonight at 10:30 p.m. I'm going to take a session on Vedantu J English, right? It's going to be the third session from the chapter chemical equilibrium. Do check that out as well, right? Okay, and do let me know exactly at what time you want the session tomorrow, right? Do you want the session on NEET at 6 or 9 p.m.? Do let me know in the comment section afterwards, yeah? People, okay, we have got one more question. We have got one more question. This is the last question. This is again going to be your homework. If you got the concept of dipole moment, you can easily solve this. You have got boron trifluoride BF3, hydrogen fluoride HF, carbon dioxide CO2, and 1,3-dichlorobenzene, right? Similarly, you need to see which of the following set of molecules will have zero dipole moment. You can solve this one easily now, right? You need to see the set of molecules where the net dipole moment is going to be zero, right? Okay. Well, I got the answer, right? I got the answer. Yeah. Do let me know its answer in the charts, in the comment section as well. So with this, people, I'm taking the leave, right? And the ones who have not enrolled into the pro subscription yet, into the actual Vedantu platform yet, I would suggest you guys to get enrolled into the pro subscription in order to avail all these benefits, right? If you're entering into the actual Vedantu platform, you're going to have 5,000 plus hours of live online teaching, tests and assignments with 10,000 plus questions will be given to you, right? 20 plus teachers with 5+ years of experience will be training you personally in all the 3 subjects, right? You have got the complete option, complete liberty to learn either in English or in Hindi, right? And once the syllabus course gets over, then we keep on having the micro course and crash courses also after the course completion, right? Okay, so how to get enrolled in the actual Vedantu platform, in the actual Vedantu batches apart from these YouTube sessions. Let me tell you, this is a video which you guys are currently watching, right? You need to click on this show more After clicking on this show more, you'll be getting a lot of links over here. You'll be getting a lot of links over here. If you want to have the CBSE Term 1 and Term 1 crash course, right? Majority of the people right here, right now are basically looking for CBSE Term 1 crash course. If you want to go for the CBSE Term 1 crash course, right? Click on this link. After clicking on this link, you need to drag it a little down. Now it's going to be your option to go for the light plan or classic plan, right? The choice is all yours, right? If you are using light plan, it's affordable as well, 2700. Use the coupon code WSPRO, you'll be getting some additional 10-20% off, right? Yes. So for example, I'm clicking on this buy complete course. I will have to add my phone number or email ID on which I get the OTP and everything and get enrolled in the actual batch, right? Since there are more links, if you want to get enrolled into the 2-year classroom program, right? 2-year. If you're going to appear in the NEET in 2023, just click on this link if you want to get enrolled into the 2-year classroom program on the actual Vedantu platform. So these are the 3 links. One is light, one is classic, one is plus, right? It's going to be entirely your choice to go for any of these pro subscriptions, right? And no, this is basically the course fee for complete 2 years if you are choosing the light plan, right? No need to pay this much of amount in one go. You can pay this much of amount in installments as well. Vedantu has kept the option for that. And at the same time, you can give it a try for a month as well. You can sit into this batch for a month, right? For 1 month pro subscription, you need to pay this much of amount, and this is the coupon code WSPRO which you'll be using in order to avail some more benefits, right? So for example, I'm trying it out for a month. I'm click on this, right? Over here, I'll be giving you my number, my email ID on which I get the notification, on which I get the OTP and everything and get enrolled in the actual another platform, right? So I think this much is enough for tonight, right? If you have not liked the video yet, please do like the video, share the video with your friends, and do not forget to subscribe to the channel as well, right? Let me see you all at 10:30 p.m. on Vedantu JEE English channel, right? In which I'll be discussing the KP-KC calculation, right? From the chapter Chemical Equilibrium, right? Yes. So with this, I'll take a leave. Let me see you guys at 10:30. Till then, you take care. Bye-bye. God bless you all and love you all. Take care, guys. Bye. Thank you, Ibra. Thank you so much. Thank you, Saqib. Thank you, Moina.